So Greg and I were working on the interaction of matter and space when we realized something. The consequences of relativity are based on the idea that space bends. But in truth, the same results would occur if space were doing something slightly different. Instead of bending, it could be changing in concentration. The question becomes, would there be a way to prove the difference? And the answer is yes. We've developed a couple of experiments that should prove whether space is actually bending, like you see in this picture, or rather changing in concentration, as represented in this picture.
The experiments are fairly simple and straightforward, but the required equipment is just a little bit out of our price range. For that reason, we're making this video in hopes someone out there with ready access to the equipment will perform the experiments. So we're going to present our case and see if we get any takers. So here it goes. Now typically the bending of space is represented like this, where a massive object like the sun pushes space away from it. In this picture, a plane of space is represented by a square mesh that's symmetrical and flat away from the sun, but stretches and curves as you get closer to the sun.
What we'd like you to pay attention to are the squares of the mesh and how their shape is changing in the bent areas, because that's what our experiments focus on. Now, is this exactly what's happening? No one really knows, because the bending of space has also been represented like this, where matter pulls on space instead of pushing on it. This picture depicts how space bends in 3 dimensions and does a fairly good job at it. Again, we'd like you to focus on the way the structure of space changes as it gets bent, going from something symmetrical to something that's not.
Do we know the structure of space is cubic as shown in these pictures? No, but the beautiful thing about symmetrical structure is that no matter what pattern that structure has, the connection points are equidistant apart. And when a symmetrical structure gets bent, those distances are no longer equal. Let's review our 2 space pictures with that in mind. Now, way out here, the connection points of space are equal distances apart. But see how those distances change as you get closer to the sun? Same thing here. The closer you get to Earth, the greater the connection point distances become.
We'll make this easier to see by comparing the 3 situations of space with some 2-dimensional drawings. Here is undisturbed symmetrical space where all the connection points are equidistant. Here is how that symmetrical structure would change if Earth pushes space out of the way or compresses it. In this case, the connection points perpendicular to the Earth would get closer, but the connections horizontal to the Earth would get farther apart. And here's how the structure of space would change if Earth pulled on space or contracted it. The connection points perpendicular to the Earth would get farther apart, but the connections horizontal to the Earth would be closer together. In either case, compressing or contracting, as you move farther from the Earth's surface, the connections would gradually all go back to being equidistant.
With these bending diagrams in mind, let's physically explain a consequence of relativity: gravitational time dilation. Atomic clocks have been used to show that at different elevations from the Earth, time changes. According to relativity, it's the bending of space that makes it happen. To understand where we're headed, we'll take a really simple look at an atomic clock. Now, an atomic clock has a radioactive source like cesium-133 in a sealed container, but a stream of ions is emitted through a small hole. That stream strikes a detector at a highly stable frequency, and a counter tallies the ion strikes to measure time. Now, let's look at a diagram from the clock's perspective that shows our connection points of space at different elevations. This diagram represents the clock at different elevations and how space changes as the clock is moved. In this case, matter is pulling on space, and the horizontal connection point distance in space increases at higher elevations. From the clock's perspective, there are less connection points between the source and detector at the higher elevation. If matter pushes on space, then the clock would see more connection points as it moves higher in elevation.
Now, we don't know if more or less connections causes time to speed up, but we do know that the atomic clock ticks faster up here. So we'll use that to our advantage. Here's our first experiment, and it's pretty simple. You take two identical clocks and synchronize them at the same elevation with their ion beams horizontal to the Earth's surface. Let them run a while to make sure they stay synced. Then rotate one clock such that its beam is perpendicular to the Earth. If space has a typical three-dimensional structure, like we saw depicted in the earlier pictures, here and here, then we predict the vertically oriented clock will run faster, just like taking it to a higher elevation. Why? In the case where the Earth pushes on space, as you move away from the Earth, the connection points get closer together. If that's what makes the clock run faster at a higher elevation, then at the surface of the Earth, the vertically oriented clock would experience closer connections than the horizontal clock and run faster. In the case where the Earth pulls on space, as you move away from the Earth, the connection points get farther apart. If that's what makes the clock run faster, then at the surface of the Earth, the vertically oriented clock would experience connections farther apart than the horizontal clock, and again, the vertically oriented clock would run faster.
Either way, if the vertically oriented clock runs faster than the horizontal clock, then space has an overall three-dimensional structure and it's truly bending. Now, if the two clocks stay synchronized, then space really isn't bending, but instead is changing in concentration because you simply can't bend a structure and only change one dimension. To be absolutely sure, a more complicated experiment could be performed using the moon. Now, the moon has enough influence to move oceans, so its effect on relativity should be measurable at the Earth's surface with today's advanced clocks. The measurement could be taken by an array of 4 groups of clocks. 2 groups in line with the moon's orbit and 2 in parallel. Each group would consist of 4 clocks, 1 oriented parallel to the Earth, 1 vertical, and 2 at 45-degree angles. If space is changing in concentration, the amount of time dilation on every clock in a group would be the same regardless of orientation. Now, if space is bending, the amount of time dilation change will be different between the clocks in a group. Now, once the moon passes over, the clocks in line with the moon's orbit would be compared to the parallel clocks for time differences.
So that's our 2 experiments. Again, we've made this video with the hopes that someone with access to the equipment could perform them. If you have any questions or would like to contact us, please email us at daveandgreg@itsallspace.com. Thanks for watching.